Shall we start, Ole? Yes, I think people will join in 5 minutes. So,
Yep.
Good morning. Good morning, and welcome to the NRIS FORTRAN workshop series. My name is Thanya Pushpadas, and I'm from University of Bergen. I'm hosting this course, and you have instructor Ole W Saastad from UIO. Before I give him this Zoom dais, I would like to give you some logistics and information. So as you got from my email, we use the collaborative document, HTOC. You can find it on the chat, Zoom chat as well, to ask question and answers, give answers. And this Zoom document, this HTOC document, you can see on Zoom now. I'm sharing it. It contains all the information about who are we. We are collaborative of IT staffs from 4 different universities: UIO, UIT, NTNU, UIB, and Sigma 2. And together we operate national HPCs and storage and gives training to our users and others. So if you want to give event notification from us, you can sign up Sigma 2 channels and the UIB HPC mailing list. And you can find the information about the NRIS documentation and upcoming training at NRIS and our collaborative training with Code Refinery, which will happen a week after next. And one important thing that in our training, we follow the Carpentries Code of Conduct. That means being respectful to each other. So if you have anything to report, you can contact me regarding this. And also this document contains workshop link to workshop page and other information. The course material we use today is linked here. And demo course also linked to the, you can find it in the Google Drive, and there is a tar files you can download. There is a GitLab repository. You can choose any of these 3, and there will be a project directory that will be, you can copy it from if you have an account on Saga that you, that I have sent you an email earlier. If you apply for it, or if you already have an account on HPC, you will get access to the project directory that we will give information further before we start the demo. And one important thing is that we are recording this course, as you might have already seen it. So, and we are going to make it publicly available via YouTube channel. So if you want to switch off your camera and not want to be recognizable, you are welcome to do that. And here in the HTOC collaborative document, you can edit this document. If you see this on top, on left side of top of this document, there is a pencil icon. You go there and edit it, and you ask your question at bottom of the page. But before we start, we have some icebreaker question and a poll for you to answer. So the one icebreaker question is list below the program that you use for your computation. You can start with the most experienced one. If you are using FORTRAN as regularly, you can start with FORTRAN and then Python, or like that. It would be nice for us to know your competence. And the poll is if you are using FORTRAN and which standard you are more comfortable with. And please type an O here, so I can type with here, and others can start with O here, and we will find out what you are answering. And you can ask the questions here, and you can go down with the numbers. We will answer the question at end each time of the break or end of the session. We will have at least 15 minutes to discuss your questions and answer. And please feel to ask any question, and we would like to have more questions. And now I would like to thank you all for joining us, and we are glad to have you here. And thank you for our NRIS staff, also our FORTRAN expert, Ole, for giving this workshop series to us. And he has like decades of experience in working with FORTRAN, and myself also looking forward to this course. I would like to welcome you, Ole, and please take over the screen.
A little background is that I have a PhD in physical chemistry from University of Oslo. And I've spent some time working in chemistry. I was working with EU for looking into air pollution scientist. My PhD was in the chemistry within ozone depletion in the stratosphere. And I worked for some time at Sintef with oil chemistry and such. And then I joined a supercomputer company called Scali, and I was there for 6 years. And we made supercomputer software because I've always been using computers both in the lab and for simulations, not theoretical chemistry, but simulation chemistry. Simulates things, and because you can change parameters, as you all know, so this is fairly easy. And 2007, I joined UIO in the supercomputing department. Now it's called IT-avdelingen and beregningstjenester in Norwegian, computational services. But I'm normally saying that we are not really doing computing. We are doing data manipulation, because all the programs that we ever come across have been memory bound, so they are bound by how fast you can move data around. Anyway, let's get starting. This thing here that we are now is, it actually started up with a question that we should provide people who are knowledgeable in the older standards of FORTRAN and make an introduction to the new things that happened in 1990s and up to 2018. And there is also a proposed standard for 2023. So I attended a course in modern FORTRAN in Umeå, and that was a lot of food for thought. So we discussed and came up with the idea that we should actually have a training that brought you up to speed with the modern things, like doing it right, variables and loops and pointer, dynamic allocation, derived types. This is for today. And then later on, object orientation and offloading to GPUs automatically and a few other things. So I'm assuming that you know FORTRAN reasonably well. And the rationale is that a lot of master students and PhDs, and at a certain point, if you do theoretical work or do simulation work, you are suddenly faced with 1 million lines of old FORTRAN 77 code, which are in a line with a fixed formatting where you have 6 places for the label number, then the 7th column for the continuation line, etc., etc. But in 1990, the standard, 1991, the 1990 standard was released, and a lot of things happening. One of them was that you have free format. You could have up to 132 characters in a line, but the newest standard, you can have a long line as practically possible. So I'm expecting that you have some expertise in numerical programming. OpenMP and MPI are, as you well know, but it doesn't matter here because I'm not dealing with either of those. And this is not a programming course, as I'm not teaching you how to program in parallel. That's for some professors who actually know how to do that and how to teach it. We'll touch upon some parallel programming in the last event and offloading to accelerator while still using ISO FORTRAN. So it's not a basic introduction to numerical computing, but I will convey some of the new, not all the features, but because there are so many that were introduced in the 90, 95, 2003, 2008, and 2018 standards. And the newest standard contains quite a lot of things. And if you are not using the latest GCC, some of the demos won't work. So, and just before we started, there was some discussion about the interoperability with C. That could be an even more for its own workshop, but I thought I should address it a little bit, that C and FORTRAN have been mixed for decades. And it's easy, but in the later years and the later standards, there have been standards for interoperability between C and FORTRAN. So you can do it right. it always been working like you see a double precision millisecond. This is FORTRAN 77 standard, external milliseconds, and then you declare an external, or in the modern version, you say real 64 and then external millisecond. But all of these are assuming that the data types in C and FORTRAN are the same. And we've been very lucky with x86 computers because they are all the same. So a double precision or a 64 4-bit real is the same. So that's fine. But if you know MPI, you will see that MPI declares their own data types. There are good reasons for that, because MPI is supposed to run everywhere, even though it's written in C and the data types are exactly the same in the computers that we so far have been using. But I discussed before we starting here that the first Cray computer had a word length of 64 bits. So all variables were 64-bit, and they only had one floating point format that was 64-bit. So you never know what you're going to get. Today it's one thing, but tomorrow's computer might not be exactly the same as we used to. So that's why the interoperability could be an issue. And that's why I'm keeping so much attention to variables and so on that will come. Just to recap that in the beginning, it all started in 1954, long before I was born. They had the formula translator for the IBM 704. But an interesting thing is that the unit 5 was for the input, standard in, unit 6 for standard out, still today. And in C, I had expected a lot of you to put up C as a language on the HackMD. I did only C, FORTRAN, and Python before I switch it off and share my screen. But C and FORTRAN goes together a long way. So that code you can see here is very old. You can even see that under the format statement there is a $sign, and this is the nightmare thing with the 77, that in order to continue the line, to have a longer line than 72 characters, you had to put in a continuation sign, could be any kind of character, in the 7th column. The punch card had 80 characters, but the FORTRAN compiler did only read the first 72. So what many people did was to put in the line number at the 8 last characters on the card, so you could actually sort the cards if you accidentally lost them on the floor, which some people did from time to time. Anyway, versions. The first really standardization was in 1966. The FORTRAN 66. It wasn't very. It was used a lot, but the more real standard was in 1977, where they fixed up a lot of things. Then the standard from 1990, it introduced free format, ISO standard, array operations. 95 put in pure and elemental functions and procedure. We'll cover that later. 2003 they put in object orientation. 2008 the major thing there was coarrays, which is built-in parallelism in the language. It never catched on. So while it is part of the standard, it has never really catched on. So I'm not going to touch coarrays, but it's a way of parallel programming. So we'll start with variables. Why is variables so important? Well, I'll say more about on this later, how we can declare variables. But in the old days, and still is, if you don't declare anything, but this is, well, you shouldn't do. You should do it the real way. But all names starting with I, J, K, L, M, and N are declared integers. All others are real. So if you don't say anything and just declare a variable set like I equals 1, then the integer variable starting with A, with I, or J or K or whatever, if the names start with one of those letters, they will be integer. If it starts with A, for instance, A equal 2.0, it will be a real variable, a nightmare. We'll see what kind of consequences this can have. So, and there were even people who said implicit real. Implicit real means that all variables name in the interval you give, A to Z, was commonly used. And not very good. And implicit none were introduced in the 1990 standard. And that helps a lot because any undeclared variables will trigger an error, a compile error. Before that, in the 477 standard, it was possible to say implicit logical A to Z. Since there are not many variables that are logical in FORTRAN, and they are not commonly used. Well, they are used, but not very often. You will, if you assign a logical to some kind of number, it will trigger an error. So if you said implicit logical A to Z, you were safe. But today, we use implicit none. So always start procedures, functions, anything you start declaring implicit none. That will flag out any undeclared variable. GFortran has this F implicit none flag that you can set, but I encourage you to think ahead and don't fall into the trap that stupid people on the internet wrote that we and my colleagues, we only use GFortran and GNU, so we don't care. And that's fine with you. But let's say you send the code off to somebody else and they are using a different compiler. Then they might have a problem. So please, implicit none, always. And there are 5 types of integer or variables. Integer, they are all signed. FORTRAN have only signed variables. So if you overrun the variable, let's say you declare it as an 8-bit variables, if you have 127 and add 1, you get a negative number. In other languages, it might be possible to have unsigned variables, but not in C. They are all signed. You have real variables. That's some floating point numbers. Complex are floating point numbers that have a real part and an imaginary part. So they combine. It's a pair of numbers. They're normally presented in parentheses around them. If you print a complex number, it will print out the parentheses and it will have 2 numbers separated with a comma. You have character and you have logical. And of course, with the newer standard, you have a number of derived types. And how important it is to have logical, to have implicit none is the little program snippet I have there. You say do 10 I equals and print it and so on. And when you have time later on, you should review the Mariner 1 FORTRAN bug. There was a spaceship who were lost because of that mistake that is present in that little 4-line snippet. So pay attention. If they had put in implicit none there, which they couldn't in 1961, but they could have put in implicit logical A to Z. That would have prevented that spaceship from falling down. Anyway, variables are not as simple as before because as the FORTRAN standard progresses, they become more detached from the actual computers themselves. So, of course, integer, real, complex, and characters and logical, they are the ones. But the message to take home here is that the FORTRAN standard makes no assumption of hardware logic nor sizes. The standard doesn't care what kind of computer you are running it on. You need to specify explicit the variables. Either a human-based approach or a machine-based approach. But most of the people using FORTRAN are not computer scientists. They are scientists in any other field. And hence, we should think in terms of humans and mathematics. When we think of, we are going to need to compute some numbers. If it's an integer, what is the largest and the smallest integer that we're going to use? And then, as a mathematician told me, when you do something, calculate something, before you start, you should think, what is the outcome space of this? Doing chemistry, you very often encounter that you have a second degree equation. And of course, that has solutions that are negative numbers. But mass cannot be negative. Concentration cannot be negative. So just even before you start computing, you should think, what is the outcome of this? Does negative numbers, are they possible? No. So you should rule out negative numbers. And then also, what is the range of my how many digits do I need in my integer? Could I run over? Could it be more than 127? Could it be more than 32,767? Or 2 billions if you are running the 64 ones? So it's very easy to make a loop, and then suddenly you want to make it longer, and you run over. If you have a byte-sized array and indexing that with an integer, and you want to address 10 gigabytes of memory, which is not too much, then the loop won't, then a 4-byte integer won't be enough. So you need to make a bigger integer. And of course, integer assigned. So here I put up the human approach. This is far too much text for a slide, but anyway. We need to think of range for integers, precision or decimals. All FORTRAN numbers are stored between 0 and 1. So they are normally point something and then up to 1. And then an exponent. We need to think, how many digits do I actually need for my integer? Then you use the function selected int kind, and you specify range. Here equals 9 digits. If you say 2, you will have up to 127. But if you say 3, that might be cover 999. So that will trigger a bigger one. So think of what range you actually need and put that in. Then you just set a variable. In my case, I4. I'm falling into the trap of thinking of like a machine that's 4-byte. But in the case of Cray, it will have 8-byte. All integer will be 8, so you should call it something else. So, but try to free yourself from thinking how the computer works inside, and use like single precision or double precision or any sensible number, or short or long or whatever for those names. And if you need 17 digit, you ask for 17. Same goes for the real numbers. You need 6 decimals and an exponent that can be at least plus or minus 20. That will give you what is in the older days being referred to as single precision. And if you want to have more decimals, you can say 15 decimal places and plus minus 307 on the exponent. And I put in how you declare such variables. And I also use how you declare constant, because there are sometimes the compiler complain that it will do a conversion from a 4-byte real to an 8-byte real. So if you really want to make a constant of the type that you declare, you can do 2.0 underscore R8 or 2 underscore I4. So this is the human approach. And I strongly encourage you to think in this term. What you can do is to take all of these numbers, to put in a module and just say use module, use the name of the module, and it's all transparent. So you only have to do it once. We can take the hardware approach. We can use a standard environment, which is quite common. And you say you use ISO FORTRAN environment, which is a standard environment that in C is all very common. And you just say integer, and you put in int64 in the parentheses. That is exactly the same as saying kind integer 64. Integer 64 is some kind of number. what that number actually is totally unimportant. And you have a declare like I did as a long int. Same goes for the real and the complex and the logical of 8 bytes for one logical. No, one byte for a logical is normally nice to have, but you can make logical in 64. So one logical is 64 bits, which is wasting 63 bits. But so that's why I always use short logicals. But that you can do whatever you like. Does it matter? Yes, it is. VAX 11 is an older computer, but it had two 64-bit format. D-float, with that 16 decimal places, but the exponent could only have a range of plus or minus 38. So if you think of the Planck constant, and in some equations, Planck constant squared, it's coming up, and that would overflow the range of the floating point numbers. And while you had G-float, which had 15 decimal places and an exponent to plus or minus 308, that will easily fit the Planck constant. So you really have to pay attention to that. So that's why the selected kind real is so important, so that you force the compiler to use the correct machine hardware or the correct floating point operations on the actual computer. And then it's a warning: integers times 4 is portable, but it isn't. It's not been standard of any standard. While there are some compilers who accept it, it's never been part of any standard of neither 477 nor any of the newer ones. So like integer 4, integer $8 are not part of any standard. So it's bad practice. The importance of keeping control over data type cannot be overestimated or underestimated. It's important for life and health. Nobody was killed in the Ariane 5 failure of launching the big rocket. I encourage you to read about this, but it was conversion from a 64-bit floating point number to a 16-bit integer. And that flowed, and with catastrophic event, the whole spaceship disintegrated and exploded. Bad enough. But the Teratech 25 incident, where a lot of people were killed because of an integer overflow. So poor programming kills people. The instructor, she told us this and that at a programming seminar at Supercomputing, that poor programming kills people, and she drew up a lot of examples where Teratech is one of them. So be careful with the range and think before you program. Before you set out, what is the outcome of this? What am I going to program? What am I going to calculate? What is the range and so on of this programming thing, my program, what am I simulating or calculating? So we'll have a little demo about the variables. I try to use the extension F90, F03, and F08. Maybe I have some 18 also, for the extension to see what kind of variables that are actually, or which FORTRAN standard that are actually in use. So that brings us over to this demo. You don't have to bring it up yourself. I thought that we could have workshop with it, but it will there are 10 demos. It will take far too long time. So I'll just bring it up so you can actually follow me typing along. This is all these programs are available. I tried to write as simple FORTRAN snippet as I could. Yeah, Mike, and yeah.
Yeah, I
Go ahead,
just wanted to
Maiken.
say, you know, remember to, you know, raise your hand or interrupt or write messages on the HackMD. I'm kind of imagining people might have questions, but maybe they just haven't gotten around to starting asking questions.
Yeah, if you have a question, please use the HackMD, and Maiken will try to answer, Tanya also. But of course, if it's very relevant to what I'm saying, just interrupt me. I think we have, if we go through the exercises fairly, if I type along here, I think we should have time enough to have some interruptions, and the exercises you can easily play around with yourself later on. So did anyone post questions or?
Noted, Ole. I just wanted to mention that you can, if you are logged into your Saga, the header document contains information where you can find this demo course and which modules you need to load. And also there are the same files are available on Google Drive as well as in GitLab repo. Thanks. Please continue. We can have a break after 20 minutes probably.
Yeah, in 20 minutes.
Yes.
So I have, yeah, okay, good. But just let me know a little bit before, because I get carried along. I concentrate on conveying the material, not really paying attention to much else. So yeah, I try to write this as pedagogic as possible, so that's why they should be easy to follow. But I encourage you to copy them and play around with yourself. Here we are already jumping in. This is already 2008 standard. I have a module called data. I always start with implicit none. You should always start with implicit none. As I said, it could be live. It could kill people if you're not doing it. So would you feel responsible if you are suddenly in a job where you are programming for a spacecraft or an airplane or whatever? And you could be responsible for the Max, the Boeing Max plane. That wasn't really a programming error, but it could easily have been a programming error. And then suddenly you are responsible for all the people get killed just because you were lazy and sloppy. So implicit none is there to help you. It's not to make lives harder. It's there to help you. Like a nuclear power plant blowing up because you didn't use implicit none. Would you feel comfortable with that? Nobody would. Well, no sane person anyway. Anyway, I made this module data because it contains a lot of things that might come in handy. I said integer, it's always been there, and I put in the key parameter, which is, and I assume that all of you were fluent in C, so I will not really refer to C to explain things, because yeah. Parameter means that the number is immutable, it cannot be altered. I call it R4, you could easily call it single precision or whatever. I call the function selected kind real. I ask for P equals 6, precision equals 6 decimal places, and the exponent at least plus or minus 20. So it's a reasonable number. That will select what we refer to as normally as a 4-byte real, so single precision. Next line is the same, just longer, more decimals, and a larger exponent, plus minus 307. I also asked for quadruple precision with 27 decimal places and an exponent that goes up to plus or minus 2400, which also works nice. But there's a catch here. If you are doing anything that requires performance, and since you're already using FORTRAN, it's already requiring performance. This is not supported in most hardware, at least not in the x86 processor. So this has to be emulated in software, and it's very, very slow. So if your program, if you actually need this, you have the possibility of doing this, but of course, it will be slow. But somebody who doing quantum chemistry once told me that you could think of she referred to one thing that you will take a supertanker and then weighing the supertanker with the skipper, then weighing the supertanker without the skipper, and then calculate the skipper's weight by subtracting those two numbers. That's easy. But then she said she was doing something more complicated. Imagine weighing the supertanker with the skipper and the skipper's hat. Then weighing the supertanker with the supertanker and the skipper, but without the hat, and subtract the numbers to get the weight of the hat. And for some, if you are dealing with this, you might need 27 decimal places. So you have the possibility, and you can easily just request that, and the compiler will select the suitable routines to deal with it. If the hardware is supported or not, it's not your call. You need 27 decimals, you need 27 decimals. Ask for it, and the compiler will fix it for you. Performance-wise, who knows? It could be slow. It could be. You could be lucky to sit on a computer who have some hardware support for this, but that's a different thing. You shouldn't really concern yourself in the first place with this. You should concern yourself doing your science right. I have a small integer that's, again, if you were using C, it will be called short or character. Short is this one. Character would be a single byte, and then 3 decimal place, 3 integer, and 999 would fit easily in here, and then 32,000 plus or minus, and then 2 billion plus or minus, and then 33 places, and I can't even think of how much that will be in normal number. So this is how you declare variables, but you feel free to use different names than I have done here, because this is related to the internal workings of the computer. Is it 4 byte, 8 byte, 16? So you should probably make some more sensible names. I think I'll update this in the future. Then I put in some math constants. I have declared a variable of type real. It's of range or size R8, which is selected kind real as above. I call it pi8. It's 4 times the Arcus tangent of 1. I also use these the constants here are 64-bit. Same goes for here in the argument for the Arcus tangent functions. Same goes for the E, the Euler constant, the exponent of 1. P in 16 decimal place, in 27 decimal places. Same for the E. And then I put on 3 complex numbers. I just call them J4, J8, and they are pure imaginary numbers. So they have a 0 on the real axis, and they have 1 on the imaginary axis. This is normally if you use the unit circle, and that will be straight up, because the y axis is normally used for the imaginary axis. This is easy. I started program variables. I use my module. This is, you see, end module data. I say use module. Then suddenly there are no private in here. So all of this content inside here is available in your FORTRAN program. I put in ISO FORTRAN environment. I also put in C ISO binding. Now we are in interoperability with C and FORTRAN, but it is the only time in today we'll deal with this, but I thought it might be interesting. Implicit none, as always. Logical, yeah, 4 different sizes of logical, 4 different sizes of integers. I couldn't find an int 128, so I had to use there were no int 128 in the FORTRAN ISO FORTRAN environment, so I had to use the I16 I declared further up. A real 32, a C float, which is exactly as you will see it in C. Real 64, C double. You see, C hasn't really come to this matureness that they are using numbers of bits required for the variable. It also have real 60, real 128, which doesn't have an equivalent in C. Complex numbers. The complex numbers are that each of the numbers are of type real 32. So there are two 32 numbers that require that it uses twice as many bits because there are two numbers. Then I have a character of length 30. And since the ISO environment FORTRAN gives us some nice things, it can do compiler version, can print out for us, compiler options. It print is printing to the screen. Write prints either to the screen if you put in an asterisk there or a star, but it can also write to any device or unit. And we remember that there were unit 5 and unit 6 for input and output, but print is always to the console. Then I use a format. Format is very much like C. If you are familiar with the C printf format, you should be fairly. But this is the same as in FORTRAN 1977 standard, so there's no different there. I print out these numbers. I also print out the maximum integers, the huge. Then we come to the thing that are only in the 2008 standards. If you want to print out the, first of all, I print out the size of those, but you can print out the real part and the imaginary part of individually, and that is only available in the 2008 standard. And then it's an interesting one, and imagine j, which or I to the power of I. So if you take the square root of -1, raise it to the power of square root of -1, you get an interesting number. While I'm compiling, you can think what's happening. First of all, I load the module. I load them on the, haha, you see? There is a thing called load this module. Load this module. So we follow the instructions. We load the module. Then we say FORTRAN variables. Hopefully this works. Yes, I become lazy, so I always just don't bother to giving it the name. So I just use a.out. And for those of you who don't know the answer to the riddle about if you take the square root of -I to raise it to itself to the same thing, we'll be in for a surprise. It's about 1/5, 0.21. It's a real number and nothing, no complex part, no imaginary part. But to go to start here, we'll see that the sizes here are 1 byte, 8 bits, and etc. Exactly the one that we specified. The C double is the same. So we are lucky here because it's always been like this in x86 that the C and FORTRAN and they use the same standard for floating point numbers. But when it comes to integers, it's a more interesting one because FORTRAN doesn't have unsigned integers, but C has. So if you want to do interoperable with C and you have unsigned numbers, you might get into some kind of trouble. And you see precision and range. For the 4-byte one, we have 6 decimal places, 37 decimals, the 37 range of the exponent. For the 8 ones, you have 15 decimal places and 300 plus minus 307, etc. And the size of the complex and so on. And here I print out the complex numbers, and you see for some of them you have quite a lot of decimals. So this was the demo, and I think it will be beneficial to see if there's any questions. I think I can go over to here. Oh, the ISO FORTRAN and ISO C-binding, they should, at least they are available in the GNU compiler. I haven't tested with the Intel compiler, but maybe I encourage you to write that yourself. It's like a module that I presented, so you can have full control. And of course, it's portable. If you do it the right way, it's portable to any FORTRAN compiler. Yeah, I'm also using all the GNU compiler. So yeah, we still have some more time. We have time to take one more slide before the break. Okay. We'll continue because we have to finish by 12:30 and we have breaks and so on. The vector syntax. You should not think like you are programming. You should think of your science. And if you operate in arrays, if your field of science is operating in arrays, think like that. If you're operating in matrices, think like that. If you're operating like in metrology and climate codes and many other things, you're operating in 3 dimensions. Well, actually 4, because you have the time. 3 dimensions. And it's quite common to have 3 nested do loops outside of each other. And think of a field. How do I, you have a cube, you have the whole atmosphere, you have the ocean, whatever, and the solution. Think of that as a field or an entity, and you don't really yeah. And think of it as a field. So you should be able to operate on your data structure, not element by element, but as a field. And to do that, we have to have arrays of different types and so on. And with the 90 standard, it came dynamic allocation and pointers. And FORTRAN is strongly typed, so there is no void pointer. So if you have your element in one type, it's quite tricky to move it to another type. In C, this is trivial. You just use void and set if you, let's say in the first C compilers before they were standardized, you could declare an character array with 8 characters, and then you sent that to a function that received a double. They're both 64-bit, so they won't crash. So you could send a character 8 array and receive it as a double, and send it back as a double and receive it as a character array, and then print it by casting it as a floating point number. And this is very, very bad programming. And of course, FORTRAN prevents you from doing that. And you can have up to 15-dimensional arrays that became available in the 2008 standards. And variables, well, arrays can have attributes allocatable, target, and pointer. And pointer arithmetic are not allowed. So you cannot have a pointer and increase the pointer like in C, like a P++, so that the pointer will point to the next element. That's not allowed. So I think we have time to start this demo about allocation. How do we allocate numbers? Here, allocate. I'll bring it up in the in Emacs so it's easier to see. Tanya, how much more time do you have for the break?
We can have this after, and then we can have a break. Ole. That would be
Yeah,
good.
we go through the allocation and so on. Yeah, here I have a program called allocatable and the environment implicit none, which has always been, should always be there. I deliberately make the J a 1-byte variable int 8, so it can only go up to 127. I have an array of integers, 2-byte integers. They are target, so they can be pointed to. It's allocatable. Even has a 1 dimension. The column means 1 dimension. So if you want to have more dimension, you have to allocate in different way. But just one column means that it's 1 dimension, but it's unknown. It's a vector with unknown length, A. Then we have another one, B, which is a vector of length 7. Then we have 2 pointers. They are pointers. They have 1 dimension. FORTRAN is picky with dimensions. So you have to declare the dimension in 1, 2, or 3 are up to 15. So you have to fix that. But we have 2 pointers in 1-dimensional pointers that can point to those 2 if you want to. It can point to anyone that is a single 1-dimensional, but 1-dimensional array. Then we called. So up until now, there is no space set aside for this one. For this, it's allocated 7 elements. Each element takes 2 bytes, and then it's 14. So we shouldn't really care about how many bytes there is. We have said that it's set aside, it's allocated space for 7 elements of the specified kind called B. And the pointer is just an address, so it's set aside place to the pointer. So in order to have allocate space for the A, we use the keyword allocate, and we allocate A with 5 elements. Then we print out the allocated vector and just null. We check if the pointers are associated. That you can check. There's a function called associated. And we put in P as either true or false. If P is associated with something, if not associated, we set P to point to A because we have already allocated A, so we can set P to A. Then we check for the association once more. Then we print out this one. This is an interesting construction which been there since almost day 1, but it still bothers some people and you have to learn this. This is called an implicit do loop. It's well known to some of you and maybe unknown to some other of you, but so I'll explain what's going on here. So what's inside this parenthesis is an implicit do loop. You have the J, which is the variable to be printed, to be used, and J run from 1 to 5. So if we print that, it will print out 1, 2, 3, 4, 5. And of course, I can also assign P to that range of numbers. So the square brackets, they will also see square brackets used. We could also see square brackets. I put it here. Sometimes you will see a construction like this. This is equivalent to this. the reason for not having this in the 1990 standard was that there was a Swedish guy in the standards committee, and he pointed out that in 7-bit ASCII, these square brackets were used a and o in the Scandinavian languages. So he made it sure that it will use this notation, but that was got rid of in 2008 version, I think. We now can have square brackets. So we fill up P, and of course with the pointer you can use the allocated just like it was A, and P and A, you do the assignment is exactly the same. So we also use, I also demonstrate that expressions are allowed with implicit do loops. We can assign it to J times J. And we print out A points to A, and we have the size of P. Then we assign Q to P, print it out again. But now we have an interesting one. This is the first time we use the vector syntax. Remember, Q is now pointing to an array, EA. So Q and A are essentially the same. It's not the one Q is just a pointer to A. So any assignment to the pointer, which means assignment to A, which is the actual target. We say A, Q equals 2. All elements in the vector is set to 2. So if you have a large data structure and assign it, a Q could be pointed to a very large 15-dimensional data structure, you can set all elements to 2. In FORTRAN 77, you need 15 do loops, nested do loops to do that. Well, of course, you didn't have 15, you have 7. So if you have if you had a data structure with 7 dimensions in 77, and you wanted to assign 2 to all the elements, you had to use 7 do loops outside of each other. And in the later standards, you could be, unfortunately, to have 15 do loops that will fill half the page. No, it will fill, well, half the page. We'll have 15 do loops and 15 do end, do, or continue loops, continue statements. So vector syntax was introduced in 1990. Then we can print out Q. It will print out all 2's. We set P pointing to B. We do the same thing. We deallocate A. We said we have deallocated A, so A is now deallocated, there's nothing. Then we say set P to A again. Then we allocate using the pointer. We set P to 4, print out the P. And then we run this little demo. I encourage you to sit down and play with yourself. So this is what we get. You remember that they were false. After we associated A, we got true. We print out the vector. We got 1, 2, 3, 4, 5. We got 1, 2, 3, 4, 5. Then we go here when I say it was allowed to have expressions here. J times J equal is set to P. We get this, which makes sense. And we point to A, size is 5. We associate P to A again, and we assign 2 with just a simple statement, P equals 2. All elements are set to 2. We point to B, and then we also set P to be 3. All elements are 3. Then we reallocated A to have a larger size. And using the pointer, we had 8 elements, and they're all 4, as we said down here. So this is the simple story about allocation. It's your call to make use of them in better ways, but this is the simple introduction to pointer. Of course, you can send pointers as parameters and such, and if you have a large data structure, you can use pointers to point to pieces of it or whatever. Will cover slicing of arrays and so on. But this is how pointers work. It's quite simple. Probably
Yeah.
time for a break.
Yeah, can we take a 10 minutes break so that you can stretch your legs and have a coffee? Shall we start then?
Yeah, we can start.
Yeah, welcome back. Just a kind reminder that please ask question and challenge Ole and also us with your questions, and you are welcome to ask any question related to this. Thank you. Please go ahead, Ole.
Yeah, we just finished the demo. We have limited time, but I'll try to explain when we come to slicing of arrays and such, it's a bit more tricky than just the simple assignment with the pointers. But I'll go through a little more slower with the next one. There was one thing I wanted to point out where declaration of variables. There are, I had a slide before about this. There are people, we put in the slideshow. There are people who use fixed numbers here because they have looked and see that the kind number here, I4 equals 4 by some mysterious thing equals 4. And I8 equals 8. And then they have come to the conclusion that they can say integer 8 by using the literal constant 8 for that. That is not the way to do things, because that only works for when the compiler author has done it so. But there are several compilers where it don't work. NAG compiler is one of them, and there are several others where they just start the numbering 1, 2, 3, 4, 5, 6, 7, and so on. So you never know what you're gonna get. So using a number there, like 4 and 8 and such, is in best case wrong, in worst case dangerous. So keep full control over that. Either use the ISO environment, or best is to use selected kind, real kind or int kind, and get hold of the number yourself, so you are sure that when it's compiled on this compiler, you get the right number. Right. We have allocated a vector and pointed to it and so on, and deallocated it. Deallocation is important, because if you don't deallocate, you might ending up having a memory leak, because if you are calling a function and it allocate and it doesn't deallocate, then you might have a memory leak, and sooner or later you run out of memory. But enough of that. Vector syntax, less do loops. We can operate on vector matrices or any dimensional field up to 15, as they were scalars. But this is element by element by element, etc. operations. But clever slicing, packaging, and shaping can do wonders. But if you say A times B, it take element, and they are both matrices. It will take element A11 and multiply with element B11 and element A21 and multiply by element B21. And of course, FORTRAN uses the first index as the fastest running. So if you have a simple array, a simple vector, the yellow do loop here, do equal j equals 1 to n, which is typically FORTRAN 77 syntax. You can set C equals A plus B. But of course, you can also just say C equals A plus B in the using the vector syntax. And for any kind of loop. But the thing is that they have to be of the same dimension. They have to have the same bounds. Otherwise, the compiler will struggle. What can we do? We can say assign, extract, slicing, shaping, reshaping, and masking. I have put up some examples here. Shape to M4. I am packing. We'll have some more about this later. And there's a packing, and you see pack takes a mask and so on, and pack can take data. That pack data to end, and masking to end larger than data one is the core function, core element in the quicksort. That is a homework assessment to play with the quicksort and understand how quicksort work. Reshaping, and of course I can say L1, which is a logical vector, and I can assign each element of the logical vector to the outcome of that test. So V4 is a vector, and if the first element is 0, then the first element of the logical vector L1 will be 0, etc., etc. We'll have some demo of this here. Demo 3, vector syntax. I'll show you the code. 3. Right. Again, standard environment. Maybe you should make your own standard environment and always use that. Or a project standard environment with all these variables set. So once and for all, this is the beauty of the modern standard. You could have that module in a separate file, compile it, and then you have a module. You just say use data, as I call mine, but use variables, for instance, and all functions, subroutines, everything would just take that, and you have full control over the variables, and you don't have to think very much if you change anything, because that's all set up in your module. So I encourage you to make a module. Some loop counters, some real vectors. I assign them at declaration time. I have implicit loop, and I don't really know if it's solved by compile time or at runtime. Probably at compile time to save time. I have a two-dimensional thing, 3 by 3, and I assign the first one to 0. Then the other one, Q, is undecided. I have a 1 over length 9, H. I have a logical array, logical vector called L, set all elements to true. I have another one, a matrix of logicals set to false. So I initialize the vectors. This is how you can initialize them. I say print out A. A is already initialized. A times 2, that will yield 2, 4, etc. And I also print out now the C, which should be the outcome of this. Then we have the logical L. They're all set to true, but B has -1, 0, 1, and 2. And I have set the elements of L will be true if B equals, if B is greater than 0. And we print that out. And we can easily, we can start off with showing how they works. Yeah, the initialization, you see 2, 3, 4. We multiply by 2. We have the vector c, which was the logarithm of a times the reason I use this is an interesting one. I is an integer, but I times a float constant yields a float. So the argument sent to log is a float. Otherwise, you'll get an error message. So it can only take real arguments. So if I multiply by a floating point number, it converts the whole thing to float. I could also use the function float on I and get the float from I, but multiply by 1.0 is also okay. Then it will take the logarithm and we'll see that it's 0, 0.69 and so on. Then we have the vector b, which was this one. We take the mask. Is it greater than 0? No, no, yes, yes. And then we say vector c yeah, vector c, we have the mask, all the numbers there. Then we print out the vector c masked. Then we have only 2 numbers. But the more interesting thing, this is fairly obvious, that we only, if we mask this one out, if we mask this vector with this one, of course there are only 2 elements here that are true, those 2. But we now you call the function size to check the size of the new vector, which is 2. So now the length of the vector b, or the length or the vector we get from that packing, from that pack, has a length of 2. So essentially we reduce the vector from a 4-element vector to a 2-element vector. So if we assign a new vector with this one, and let's say we allocated, we could use size of that one as an allocator, and then suddenly we will have a vector with only 2 elements. So it reduces the size. Then we can continue with the where construct. We can put them side by side. Where b equals or are greater than 0, we'll take the square root. Makes sense. Elsewhere, we take the square root. We just cut off the negative number, so we can take the square root anyway of the absolute value. We just set the absolute value. We don't take the square root. We just set the absolute value, but we could easily put that into the square root. But I wanted to put in that you see that we are here, and then it actually went into this branch, and we print out the vector b. So we get 0, 0. We get 1, 0. Here we had the absolute function. Here it's hard to tell because it was equal, so it's square root of 0 or square root, yeah, in the absolute value, because it's not greater than 0, and 1 and the square root of 2. So that works fine. We can also say, make a single line where b equals are greater than 1, set b to 0. And greater than 1, it's only a single place. This is the element number, the last element is 2. So here, where b is greater than 1, we set b to 1. So it will affect that element that matches that condition. So this is a very powerful way of dealing with vectors. And of course, it can do. Next one. We can take vector c. We can put in here, we can put in a where it's less than 1 or more than 0.6, it will be set to 1. If it's more than 1.1, it will be 2. And you'll see it changes the values accordingly. So this is something you don't have to familiarize yourself with. Run the examples, write your own examples, and spend time playing with it, because it's the only way of familiarizing what the where and so on, and the masking and the vector construct can do, vector syntax can do. I cannot really put that into your head. I can show it to you, I can explain it, but you really have to familiarize yourself with all these wonders that you can do here. We can do matrix manipulation. Assume we have a matrix M. And what is the matrix M? We already printed it out. It's just 0. Did I put it to 0? Yes, I did. M equals 0. And it's a real, so it's 3 by 3 and it's 0. And I print it out. I use 3 numbers in a row. This 3 here is just, well, formatting I expect you to know fairly well. So matrix manipulation. I want to have the first column is set to 1. The second column is set to 2, and the third column is set to 3, which is this one. It works. Column major. Then we can do a bit more clever thing. We can run an implied do loop. First of all, we set M to 0 again. I run through a do loop here, but I run through the first index. The second index, I use an implied do loop here, and I said A plus J for I equals 1 to 3, fill row by row. Then I set Q to M for reasons further down, and then I print the M, and the implied do loop will give us this one. We just add those together. So another one, we can extract the diagonal. Extracting the diagonal requires the pack function, which we haven't covered yet, but we'll do later on. We take the matrix M, which we already have up here. We collapse it to a vector. H is the M collapsed into a vector. All elements, because of the true, all elements in the matrix are collapsed to a vector. Then we print out every fourth element, 1 to 9, but increment by 4, which is essentially starting with the first element and then go through diagonally, because we increase the column by 1. Then we have the diagonal. Then we can mask the diagonal in the matrix. by setting L to true for the main for the diagonal, and then we can pack it again, and then we can see that we have it masked out here, which gives us 2, 4, 6, and then then that's the matrix, the diagonal. But then I did something interesting where it's not here. I set when it's not L2, I set it, this is diagonal. The L2 is here, true, 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 so it's the diagonal. I set all elements that are not on the diagonal to 0. And then I divide it by itself. I could easily have set it just to 1, but I divide it by itself to show that you can divide. Then we get in a unit matrix. So here is a lot of things, but there are many, many more clever things that I never thought of that I just want to touch upon the small introduction. So next one is function operation. We have the matrix again. That's why I said that I copied the A to Q, so I can say M equals Q. This is again a syntax operation. All elements in M is set to all elements in Q. We print out the M function operation. I take the square root. I said where M equals 0, take the square root of M and assign it back to M. Print out. I say M equals M to the power of 2, which the essential just nullifies the square root. Print it again. And you see the original square root of all elements greater than 0. They are all greater than 0, so that's fine. Then I didn't time it by itself. That's a mistake. I timed it by 2. Bummer. But the correct is in here. Yeah, I raise it to the power of 2, and I get the matrix back again. So there are a lot of things you can do here, and with the vector syntax, and this was introduced in the 1990 standard. So for those of you who haven't used it, it's a very, very powerful tool, and I just scratch a little bit on the surface. There is so many clever tricks you can play here. So yeah, we have limited time, so otherwise I could have many more. I don't look on the HackMD to no questions. Good. If you have questions about this vector syntax, it's possible to come with a couple now, or we can take later on, because it's going to be even more tricky than this. Slicing, like slicing out a piece of meat or a piece of cheese or whatever, and yeah, manipulation of arrays in modern FORTRAN style. This is the demo about slicing of arrays. This is also a bit tricky, but it's so cool that all these nice things you can do. For slicing. Sorry. Again, implicit none should always be there. I can't say I should set aside, I should put myself on repeat for 5 minutes. Implicit none, never leave home without it. I have a matrix 6 by 6 and a 2 by 2, and everything is on integer, and I have some constants here. I are using reshape just to get this one into a sorry, into a matrix. We'll come to reshape later. So this is just a vector of 36 elements. I could have used an implied do loop, but this is a way of showing you can do it manually also. I could also put it up in here. And then I feed in a vector to reshape. And I say the shape of it is 6 by 6, which is coincidentally the same here. I could have used variables here, so it's more portable, but this is for for demo. So I also do it some manually. I will run and go to the code at the same time. So we get the matrix 1, 2, 3, 4, 5 up to 36. Then we pick out one row. We slice out. We want to have the first column. No, the first row. Sorry. We fix the column to 1. We put in column, which will be like a star. Think of it as a match for everything. The whole column and the whole row. Sorry. Then we get the first row. We want to have the first column. We just change from column and the first row. We have the first column. Easy. Then we take the diagonal, but that's not so easy with slicing because it's matrix. So if we wanted to do it the way I did it in the previous example, we had to pack it, unpack it to reshape it into a vector. But we can do it with an implied do loop as easily. We can just say y1 I and then run through n. And then we get the diagonal. It's another way of doing the same. So you have now 2 ways of slicing out the diagonal. This isn't as elegant as the first one because this is a do loop, but it's a nice way of showing how you can use an implied loop. Then we can take every second element. We take first column and to n, but we step by 2. Every second element with a smaller matrix because it's only half of it. We can combine elements. We can merge these with this matrix, Z matrix. Z is 0. And we can do it for all places where it's less than 5. And we get this one. Only for R less than 5. Then we can make it an upper triangular matrix. We need to have a loop here, unfortunately, but we can easily take everything that is less than this triangular with this little baby. We say we go to 2 to n, and we use this column, and on the other columns we go from 1 to L to j minus 1, and we have it upper triangular, lower triangular. This is way of slicing, but this is not really doing any of the fancy function. This is you could do in the older standard, but it's an interesting way showing that you can slice up of elements. Then we extract a small 2 by 2 matrix, which you can do with a clever way. We just say that A equals, take out 3 to 4, 3 to 4. We print it out. We extract the small one, this one. It is contained in here. Then we can update the submatrix. We can say that those little submatrix are to be multiplied by 6. You see here, the numbers here are multiplied by 6. And of course, there are some maximum value, minimum value, and product. And here I put in a mask also for those where it's less than 15. So minimum value, maximum value, and product of for the number less than 15. So this slicing is here is slightly more tricky, but you really have to sit down and play with this yourself, because it's a combination of merge and pack and shape and so on. We'll come to shape and so on later on. But I've tried to use this vector syntax as much as possible, so to convey the message that you can do a lot of things with vector syntax to slice up of fields and matrices and so on. So there's only one way of learning this, is to familiarize yourself with these functions. So some questions about this. That's easy to answer. String or character. So it's a format sign for string or character. Right. More vector of packing, unpacking, masking, shifting, rotating, locating. Even more tricky. Modern FORTRAN mask equals V1 different, not equal to 0. In FORTRAN style, one thing is that you have to write a lot of more, but this is overcomable. To have nobody has problems of writing code, but the point is that you have to know n. In modern FORTRAN, you don't know how large these entities are. Mask and V1 can be they have to be the same, but they could be of any shape and any length and any size. But on the lower one, first of all, you have to know that V1 is a single dimensional vector. Otherwise, you have two loops. And you have to know the n, how large it is. In modern FORTRAN, you can easily get the n by just saying size of mask and size of V1, but you don't have to. You don't have to know that. You can only see the mask is all elements. Mask is containing all elements that are not equal to 0, which is much easier. Let's say you want to take a square root of a large thing, and it's also a variable size. You have it in a function. You don't really know what is the size when you program. And you don't want to take the square root of 1 because that will trigger an exception and probably halt your program. So you put in a mask. Or you want to divide, because division is typically non-zero. And you just use the mask to update the elements. If you were in 77 style, you had to know the n and the m size and all the sizes of the field. If it was 15 dimensional, you will struggle because you will have 15 loops. You will also have to write one function for 14, 13, etc., etc. In modern FORTRAN, mask and put it to any kind of test. So we can go to the demo 5. Also add it to the 5 pack. I think there is only one here. It's called pack. Yep, square brackets was added to the language in 2003. That probably because of that Swedish guy retired. They saw their opportunity to introduce the square brackets. So now you can write a vector, constant vector with square brackets, which is much easier than to have the. I never really liked that syntax too much. I understand fairly well why, very good while it was not used, because A and Ö, no, A and O in Norwegian and Swedish and Danish, but yeah. Now I think we got 2 files. Right. And pack. It also compiles. So we allocate a vector 1. Lengths, they are fixed vectors 1 and 2. This one is allocatable, so it's unknown at compile time. This is a small matrix 2 by 2. Again, a mask vector, length 6. And it's also a mask 22, which I set to true. And I have a character variable called form, which is for the formatting things. Make it easier to format this, just set to A, which is A is for strings or characters. 6 means that there are 6 repetition of the I4, which is for integer, with for basis for places. FORTRAN is a bit unforgiving. If you put in a number with 5 digit, you will get stars, asterisks, and stars. So it will not just expand. So here is a mixture of write and print. Write star means that it's standard out. Print is implied standard out, so you don't have to, it's always standard out, so you don't have to bother. But write, you can put, I could easily put in a unit number here and write to a file, which we'll cover later on, how you can do that in different things. So here is the one I showed you. The mask equals all elements of V1. V1 is set here. So the mask will contain true, false, true, false, true, false. And then I put in the diagonal of the make it, the M1 is set to 0, and I enter those 2 numbers to make it an identity matrix. And we'll take the first lines. Here, V1, 0, 1, that's already have. That mask will then be true, false, true, false, true, and false. Then we pack the V1 vector using the mask. We'll get 1, 3, and 6. Then we pack it with all elements that are greater than 1. The result is 2. And then we take the size of that one, 2. Then we set V3 equals to the package of that one. And we get that size equals 2. So how did we do that? First of all, we said size pack that one where we get 2. Note that the side reduced the result of it. Then we print out vector 3, pack v1, v1 equal or greater than 1. Okay, since the size of 3 is unknown at compile time, we need to declare it as allocatable. But now we know the size of 3 because we have this one here has already been printed here, and it's 2. So now we allocate v3 with the size of the packing function from v1, which is a neat trick. And then we assign v3 with this one. Because now we can do that because we have allocated it. So there's set aside space for it with the known size, which up until now has been unknown. But we allocated it with the size we calculated from here. And of course, this size does not depend on the length of vector v1. It does depend on the outcome, which is depending on the content of v1. So if we change the content of v1 to all numbers greater than 1, the size will be different. And the size of the allocation here will be different. So this is a way of dealing with the unknowns at compile time and fix it at run and do it at runtime. So now we can print the v3. It contains 3 and 6. And it has a size of 2 here. And we deallocate the v. Then we go to next. v2. We pack different from 0. 1 is different from 0. Okay, that goes into the new vector. 0, no. 0, no, but 2 is. So we have that goes into the new vector. But we can even do better. We can also say that for the numbers that are false here, doesn't match here, we take numbers from this other vector. And since that those will now be in position, later positions will be taken from here, which is a tricky one. So you'll see it will fill up the vector first with the ones that are greater than 0. And then it will fill the rest of the vector with elements from this extra vector here that we put in. So we now get a vector 1, 2, 3, 4. The first 2 wasn't used, and then it takes the 2 others since they're already there. So it takes 3 and the 4 to put in. It's a neat little trick. Same here. We have taking where they are greater than the first element. And we get 3 and 6 because it's greater than 1. We have less than 1, less or equal to 1. We only get 1. Then we pack where v1 equals to 0 with the input vector to be used here. And we see that there are 0, 0, 0, and 3 new elements. Because of the original vector, there were 3 zeros, 1, 2, and 3. They will be put in there, and it will be filled up with the corresponding elements 7, 8, and 9. So pack is a very, very powerful function. Then I'm having a mask, true, false, true. This is the old mask. And then I put in this vector here. 3, 4, 5, 6, 8, 9. You take 1, 3, and 6. Those 3. And that fill the vector with 3 elements. So we need to find 3 more elements to fill the vector. And that is taken from the input vector here. Fill it up with those. It's not very it's not intellectually very hard to understand what's going on, but to familiarize with it and actually sit down and write that code yourself need practice. You really need to practice with this and know when suddenly this is extremely smart. Most of the time you don't need it, but suddenly you are facing a situation where it turns out, wow, oh, didn't I see something with this? I could match out and slice out the vector element that fitted a test and then fill it up with some extra. Anyway, that part I can't do. I can only convey these messages and show you the examples. To familiarize, it's need practice. So you have to set aside practice to play with these functions. 2x2 matrix. As we know, I remember I put it in as the identity matrix. I collapse it into a vector, pack M1, so it becomes a vector. Here, pack M1 with true. That results in a 4-element vector. I can unpack. I have this one again. This one we know, true, true, true. And I use the mask, and I have -1. It is false. It's number 2. 3. It uses the original vector. 4. Oh yeah, this is false. So I take this one. So this is doing it in another fashion, element by element. And then we can go to matrix 2x2 to a vector by unpacking. We now have this one, v2 equals 1, 0, 0, 2. Then I unpack with a 2x2 true mask, so everything is true, and use a 0. And unpack v2 mask 2x2, all elements true, and 0. I'll get only those 2 numbers. And then we can shift. We have a v1 again, 1, 2, 3, 4, 5, 6, 6. Here, I shifted 1. So, it also, this one is rotating it, so the 1 will be there. 2, so the 1 I shifted to the left. So, and the 1 will just come around, rotated into to the end. If I do the other way, you'll see that it shifts the other way, and I can also shift with more elements. So you can shift both ways. So nothing is lost here. You just rotate the vector around. You can also do the same thing with the matrices. C shift. I shifted those 2. So now you see the diagonal is coming in the other direction by shifting. And you can easily imagine how complicated this can be on a 15-dimensional field. But that could be extremely powerful in many situations. We can shift by adding element. instead of just returning them in rotating, we can shift out so they are lost, and the element that are lost are replaced by this constant. So you see when you shift 2 times plus, you introduce 2 minus 8s here, and if you do the other way, you get the 2 here. So that's another way. The last one on this session is the location. We have a vector here, 3, 4 up, and we want to find the location of an element less than 6 maximum, but only elements that are less than 6. Okay, 3, no, 4. Well, that's yes, but 4 is greater than 3, so yes here. But 5 is greater than 4, so this one. And it's not, and it's less than 6, so 5 is the one. And 1, 2, 3. So this element here satisfy this one. So location number 3. There are no elements here, 1 and 2 there, so you have to run through all of them. But you see less than 6, it's only 5 who satisfied, and 5 is the greatest of those that are less than 6, and that is found at position number 3. And we feed that one into the as an index in the vector, and of course we get 5. As you see, there are so many clever things that have been introduced with the vector things and the packing and unpacking and so on, that that is sometimes mind-boggling, especially when you think it's in up to 15 dimensions. How on earth would the shift work in X dimensions? Or how would you pack out and filter out with masking and so on in all these dimensions? But there are people who program in such dimensions, and some of them are very happy with this. So that's your call. I can only show it to you in the simplest form, and you have to familiarize yourself and become experts. And sometimes some of you might be able to show us some examples of high dimensional things. So that brings us to the next one. Unless, well, I can.
Can we have a break now?
We can very much have a break.
Yeah.
Oh, yeah.
Welcome back. Ole, are you ready to continue?
Yeah, I'm ready.
Yeah, thanks. Please go ahead.
Yeah. The next one will cover shape, reshape, and pack again. And there are even more things that we can change the shape of vector of any dimension, massage them from a single vector to a 2D to a 3D to a n times n, and of course in several dimensions. There is no end to it. So we just go at it, and it's number 6. So I've already brought up the shape here. Shape. Program shaping. 3 integers, and they here it's just a integer. I've been lazy, and that's a default variable integer, and of course a default integer depends on the people who wrote the compiler. So what is that? Who knows? Could be anything. It's up to the discretion of the author of the compiler, so we don't really know what we are going to get. If you have any interest in knowing that your integers are long enough or whatever, use kind. Use the selected kind integer with the numbers of the digit you want to have. But By default, integer is a 4-byte one, so it goes to 2 billions. But it's easy to get over that. Suddenly you have a negative length of something, you see that you have run over the limit. I use, again, a character of length 10 called form, short for format. You don't call it format because format is a keyword, so it can mix up. We have some integers. This time I just declare them here. It's possible to do this. This is the same as saying dimension 2 by 2, but I have different dimensions on several of them, so I was lazy also. I put in the dimension here. This is not really kosher to do so. So if you want to be nice, you will have a one line for each here. One line called dimension 2 by 2, and M1, M0, one line called integer dimension 3 by 3, and M1, etc. up to M4. But I was lazy, I did in one line, which is okay. And the same with the vectors. Then I'm also a bit tricky here. I have a few vectors more. I have 3, 4, 5 vector, which I assign to 1, 2, 3, 4, 5. This one is interesting. It goes from -2 to 2. And it goes from 0 to 8 by increment of 2. But this is the implied loop, so that's easy. And then all elements in L1 is true. So I put in simple assignment. The vector M1 is reshaped from V1. M1 is reshaped from V1. Okay. V1 is 9. It's 9 elements long, so we can assign 9 to it. Then we can reshape that 9 one into a 3 by 3 because 3 by 3 is 9. So we can easily reshape M vector V1 into a 3 by 3. We are not allowed to use this kind of syntax. It's not allowed, unfortunately. So we can run this one. Yeah. V1. We set that one. Vector V3, 4, 5, and M L1. But I set L1, I set all to true in the beginning. But here I set L1 to be vector 4, where elements are 0. And V4 was this one. It goes from -2, -1, 0, 2, 1, and 2. So this is fine. So they should only have one element, which is this one. Yep, so this is right. Then we are calling for shape of M1. Call the function shape of M1 that return 3 by 3. We call for shape of M4. M4 was defined up here as 2 by 2 by 4. Yes, 2 by 2 by 4. And then we can do sub things. We can say M4, the first column only. That will give us a 2 by 4 one. We can say the first column and the first line, that will give us a 4. So we can extract by saying this. We can extract submatrices and even vectors. The first we reduce by tripling this, we reduce the number of dimensions. And we also just pick out one line. And well, now it's starting when we have 3 dimension, it's easy to do X, Y, Z. So this is the X dimension, Y dimension, and Z dimension. So here we keep the X and Y fixed, and then we go up along the Z dimension. For those of you in climate, it will be U, Y, and W, if I recall, because U and V was wind in the normal direction. W was in the up direction or down direction, which is generally smaller. Anyway, I haven't been involved in this for 20 years or something. Yeah, printing out 9, I3, and L3, and so on. That brings us to printing out the first row of M1. M1 was a 3x3. Yep. And it was reassigned here by 3x3, so it 1 to 9. So the first row is 4. It's 1, 4, 7. 1, 4, and 7. Yeah, that's the first rows because there are 3 in each row. Yeah. Size of the V1 was 9. Size of the M1 is 16. Which seems a bit strange. Size of M, here is a spelling mistake. Size of M2 is 16, which makes sense. This is 4x4, and 4 times 4 is 16. So there was a mistake here. Sorry for that. I really have to update this later. And then we can take the size of 1, 2, 3. Of course, that is 3. We can take size of V2, which is had a bit longer. V2 was on length 16. This one. Of course, we take size of V2, but we only take every second element. Size, of course, is 8. And then we slide out every 4th element. Go from 1 to 16, but every 4th element gives us this one. Every 4th element. Then we take an implied do loop and fill it up with numbers. This one, we could have done this with pack and so on, but easy to fill up with just 2 implied do loops. That also can show that you can 2 implied do loops together. And yeah. Then we set V1 to 0. We update the diagonal to be all ones. And then we reshape the V1 into M1. And we print out M1. Here we update the diagonal. We get 1, 1, and 1. And we convert that into a matrix. We get the identity matrix. And then we go on a different one. We take the V2, which is a longer vector of 16. We reshape that one into a 4x4 matrix, the M2. Then we print out the matrix just to see that it's working. And then we do something clever again, as we have already done. We assign M1, which is a 2x2, to the core elements 2 to 3 and 2 to 3 here, which is the 6 and 10 and 7 and 11 elements into the M1. again, slicing and yeah, that was a slicing one. Then we collapse M1 to a vector, which was this one. And then we take M2, which was a bigger one, and reshape to a 2 times 8. M2 was a 4x4. Here, M2 is 4x4. I think we have that further up somewhere. Yeah, M4, M2. M2 is 16, so it's a 4x4. Then we reshape that one into a 2x8. So M2 is 4x4. We shape it into a 2x8 and print it out. Yes. In 2 times 8. We reshape 2x2x4 printed as a 2x2. So now I've also changed the M4 and the one that into the M2 into a 2x2x4 with using reshape. And then it's also easy to print a 3-dimensional structure, so I printed it at 2x2. But you can print it in any way you like, or even as a vector. So the shaping and reshaping and so on, and combining and extracting and masking and reshaping is very, very powerful tools. So the whole language is now based on vector and array and matrix operations, so that you can, as I said before, you can think in terms of your science and much less about nested do loops. You should be able to operate on vector fields and matrix fields and so on, or even cubes or data of different type, and not being too much bothered with the do loops. Make it much easier and easier to port, because the size and shapes and so on doesn't really have to be known before you start running. Sorry. So that brings us over to, I can open, see if we have some tricky questions. No. It's doesn't require much knowledge, this one, but it requires that you actually think and pay attention, and that's the easy part. The hard part is that you have to go home and play with this yourself and familiarize it with the function, so that when you are sitting here and programming, you will know by the top of your head, wow, here I could use one of these modern new functions. We take the next slide. Now we are not really done with arrays and fields, but it's so powerful, so we need to spend even more time. But of course, from FORTRAN 90 and onwards, there were new control things in loops. Of course, they had computed go-tos and all the nasties in the older standard, but modern loops now have while loops, and you have exit and cycle and case are new types of keywords. Of course, we have the old do loop, where you can actually run j equals 1 to n, but you can also have a do while, where you don't actually need to use the word while, but you can just say do. That means do forever, and then have control structures inside where you can either exit or cycle. Exit, of course, exits the do loop. Cycle is an interesting one. It will force the control up to the top again. So it will stop this iteration and continue with the next iteration. So, and case are that we all know from C, which is called select in FORTRAN and so on. And yeah, we'll We'll have the number 7 demo. Control structures. There is not much actually to come with theory with this one, because they can only be explained by examples, because explaining what the functions do doesn't really make sense. Control flow. I put in an interesting one with temperature, because my old programs with thermodynamics that I wrote during my PhD, my doctorate in chemistry, they were all having do loops starting with T equals 273.15 to 373.15, and T was double precision. And it was all nice until 2003 standard, when that was disallowed. Today, the loop counter can only be integer. Bummer. But there's also a couple of other nice tricks with yeah, I don't have it here. I have another one. It's with an interesting one. We have a do loop. This will run forever. And do, this loop is a infinite loop. And of course, there is no increment, there is no I++ in FORTRAN. You really have to write what you mean. There is no I or I minus minus. So you have to write this in this way. And I set A to 1 in the beginning, B at 1, and I and J are just loop counters, and 1 equals 1, and temperature equals 0 degrees centigrade, and there is a C for centigrade. So the first loop is very simple. We can compile this one. Control structures. And of course, you see most of the program up until now have been F90. So they're only the 90 standard. Okay. Infinite do loop, cycle and exit. If A equals is less than 5, cycle. So it shouldn't do anything. It shouldn't print anything. It shouldn't do anything. It should just say, go cycle. So go up to 2 again. And if A is greater than 10, exit. So it will continue to the print statement there. It will end the loop. So it will print. It will not print anything until we get to 5. But as long as A is more than 5, but less than 10, it will print. So it will print 6, it will print 5 up until 10, which it does. Okay, good. Then we have a while loop, do while. Here we have a while loop with a test. So this loop will run B equals is less than 3, print B. So now comes the thing that you can think. Wouldn't a real do loop for B equals 1 to 3 do the same? What's the difference? If you keep that in mind, put it in your local look-aside buffer and keep it there. So we'll address this later on. But it's obvious what this is going to do. This is so simple loop. It doesn't require much to understand how this works. So of course, this is printing 1 and 2 easy. But keep this in mind, because it can be interesting, because in each iteration of this loop, there is a test. This is just like in C or whatever. Each loop, each iteration of that loop includes a test. Tests are costly, so hence we try to avoid them. But we'll have an example about this later. Then there is the temperature loop. Here we have to do a while loop, since the loop counter with normal do loop with the loop counter cannot be done. So we have to do a while loop in order to have a real counting variable. So as long as t is less than 300, then we just convert to centigrade and we print out. I done mod 10, so I have less temperature to print out. I print it out with the centigrade and Kelvin and so on. So this is fairly trivial, but it's a way of showing that you can have loop counters with real numbers, but you have to use a while loop to do so. I could not say do t equals 300, 400. And since t is a real number, it's a real variable, it will not compile, it will complain. Of course, you could force the compiler to eat it if you give it the right flags to adhere to older standards. So that's also with FORTRAN. Any 1966 thing will compile if you just throw the right flag. If you give it standard equals legacy, it will eat anything. So yeah, but try to avoid that. But you can also mix and match the older, if you have an old program with 1966 or 77 standard, you can also put in new stuff. But if everything is written in capital letters, you might be well off by using small letters for the newer stuff, so people can see that this is the newer standard. So the while loop can be in with the counting variable in double precision or whatever you like to have in real. Then we have the select statement. There's a simple do loop. I just to make it simple to explain what select and case means. So select statement, if it's 1, I print 1. I said, and also I just said I equals 1 here so that you could see that many lines of code are allowed. You can have a whole block here. You can have as many lines as you like here, call functions, whatever. So just to illustrate that it's allowed to have several lines. If case equals 2, then I print 2. And if it's something else, it's using the default case, it print many. And of course, since this one runs 4 times, it will print 1 because it's equal to 1. And remember, I had 1 further up here. I had 1 equals 1. That's why you can have a variable also. Don't have to, I would explain so that I wrote it deliberately so that you can show that you can have variables here. I haven't tried changing those variables within the loop. Could be interesting to put in 1 equals 2 or something, or 1 equals something here and see what's happening. That could be an interesting one. So yeah. That's an exercise for you to play with the select case and so on. But back to the loop, the control loop. This is nothing new, but this is an important thing. If I asked you, I actually did that. There was an interview once where this guy said he was an expert in FORTRAN, and they called me in, and I said, you know, I wrote this one. I wrote this one on the blackboard without the print. And I asked how many rounds would this loop run? And he failed miserably. Many of you might say that it will run just once, but it won't. It will run 3 times. Remember, I talked about the test, the while loop. In order to achieve peak performance, the FORTRAN compiler, FORTRAN language standards, And compilers, people who write compilers have figured out that if you set up a do loop from 1 to n, you probably want to run the do loop from 1 to n. So there is no test. It actually runs the number of iterations you asked for. So if you set the j set the end statement and the end of the loop to anything like I do here with 0, it doesn't matter. It runs through the loop regardless of what you set the end point to. It will run. It will start iterations from the first time it hit the do loop. You'll see that I'm going to run I from 1 to 3, and that's fixed. When you enter the do loop, it will run 3 iterations regardless of what you set the j to. So it's an interesting one. So if you have a test, tests are costly. So they will try to avoid having so many do loops and so many loops there are in FORTRAN. It's actually a loop language to run through data structures. Having a test would hamper performance severely. So it will be very, very bad to have any kind of tests within a do loop. Like C, they have a test in the loop. You see, you have 3 statements in there, and at the middle one is generally a test. So, and tests are no good. Tests are costly. So you're better off by masking. If you want to take the square root, make a mask, or whatever, it's much more efficient than having tests in a loop. Let the compiler people and let the compiler do the optimization for you. So this is control flow. You just have to familiarize yourself with the concept of cycle and exit and do loops, which are infinite, while loop with a test. I have 2 different while loops here. And then the select statement, which can be quite nice, especially when dealing with, let's say you want to deal with the input from a user. And users, my programs are simple. If I ask for a number and the user give characters, the program stops, aborts. But if you want to make sensible use of inputs and options and so on, you are easily into the select type thing, select case, where you can deal with all kind of nasties from the users, which in some cases are necessary. And of course, this now the do loop. So I can go here and we can see if you have some. Yeah, so no tricky questions. Good. I hope it's okay with you. So yeah. Another thing that was introduced in FORTRAN 90, I clipped the one that could be declared and used freely. It's a strange sentence, but I just clipped that one from the standard or from internet somewhere. Recursive functions and subroutines, well, functions. You can also write subroutines, but the functions are the more normal, and most of us have known like the product thing like fact function and Fibonacci. Fibonacci is the most used, and you can write it so easy, and it looks so nice. Fibonacci numbers are defined by this formula, and you just write that formula. The only thing you have to deal with is the fact that when n becomes small, sooner or later we have to a special case where n equals 2 or less, then you have to do something. And for all other n's, you just call -2 and -1 and let the recursion take the rest. And there is also an example of a quicksort, which I did not write, but that's an exercise for self-study. And I also have an extra exercise for you for writing that quicksort, because quicksort is also nice. first of all, is to understand the quicksort, how it's working. And then we'll come to the next exercise using quicksort. But first of all, we go to recursive functions with the Fibonacci, which is it's how many rabbits you get, if I don't recall, if I remember correctly. I also have another nice one up my sleeve for you with this one, but demo 8, we have 10 demos, so I think we should be able to finish in time. Fib, it's also 9, FORTRAN 90. Here I also deal with argument from the users. Oh. And FORTRAN environment, implicit none, never leave home without it. Integer, I use a small integer because for Fibonacci numbers with anything larger would take forever. I have a character length of 10. This is the command line element, the command line argument. It's a character buffer. I call get command argument. I can't recall when that one was introduced, in 95 or 2003. Anyway, command line argument, you don't have to deal with that. And of course, you can also call how many there are, but normally you will know how many there are. And if it's just a little bit different, just abort or print out the help or whatever. I ask for argument number 1, which is the 0 argument is the name of the program. I ask for 1, and I ask that to be read into a character array or a string. FORTRAN doesn't have the notion of strings. It's a character array called ln, which is short for line. Then I do something cool here. This is the first time I show it to you this time, is that I read from an internal file. This is the same as doing scanf in C. I read not from a unit, which is connected to the outside world, like 5 and 6 for keyboard and screen or display. I read from a buffer. So I apply the read function from the buffer, and I use it in free format, and I convert it, try to convert it to an integer number. If I give it characters, it will abort. So I should, in principle, put in 1 page of things here to test that the actual user is giving a sensible integer. But I didn't. I didn't care. But you should think, does it need to be, do I need to take care of the user's input or don't I? But this is nothing to do with the newer things in FORTRAN. This one is, I call the Fibonacci function where I use an implied do loop here. So I do it for all the number, for a few numbers. I could just input a number here, n, but I wanted to put in a more than one, a small loop. But in principle, I could just say fib of n and get the numbers out. But now I get more numbers. So simple. But then the nice trick here is that this is the function. So here is a lot of nastiness. It's a pure function. Pure means that it has no side effects. So there's nothing going on here that can change any variables outside of the function. It's possible to write side effective functions that can update variables and so on. That's not good. Pure, no side effects allowed. And recursive mean that it's a recursive function, so it will have, each call will have its own stack. So if you don't put in recursion, it will fail. And because now if you put it in recursion, it will allocate memory for each invocation of the function. Fib of n and result f, standard environment, never leave home without it. And integer 16-bit, intention in. So the function argument here have only an intention in. So if I try to update that one, if I assign n to something, no, assign 2 to n, for instance, or try to update n, it will not be accepted. So using intention are very, very important. You should always use intentions when you are dealing with functions and subroutines. It can save you a lot of troubles. It will save you a lot of trouble. Intention in and out and in out. If you have a variable coming in on a subroutine and you do a lot of things and you want to send it out again, then you use in out. Here I use in, and then I have the f, which is the result I put up in there, the f. So if it's less than 2, it's the same as n. If it's greater than 2, I call n minus 1 plus n minus 2. I have to put in integer 16 here because it complain if I add a 4-byte integer with a 2-byte integer. So I set them to 2-byte to make sure that it's no warnings. So we can run this one. Yeah. I need to give it a number. 1, 2, 3, 4, 5, 8. Give it 6. One more Fibonacci number. Give it 10. If I give it 20, it will take some time. If I give it 30, you see? Some interesting things happen here. It goes nice up to 28,000. But after that, it fails because I have said integer 16. That goes only up to 32,267. And anything more than that will wrap the most significant bit, make it a negative number. So it goes wrong. So that's a nice that we could show that. And so maybe we already killed people by doing this mistake now, by asking for 30. So if you have an input check, you should check that the input is always small enough to accommodate for this. See, 25 was too much. 20, okay. 21, yes. 22, yes. 23, no. So if you want to write sensible input check, you should check that the input is less than 22. Because otherwise it will wrap the integer range and cause a failure that kill a patient, potentially, or down an airplane, or blow up a nuclear reactor. Make your choice. So having full control over the range of the variables are very, very important. So we should, I'll show you well, I can just show you the quick sort. Quick sort, it's contains recursive function quick sort. This one you have to really sit down and play with it yourself. So I'm not taking it up in the editor. This one, sit down. It takes some time to understand it, but it's very nice when you suddenly have understood it. It deals with real numbers. So there is a function called quicksort reals. So I didn't write it, so that's why all this text is here. So, but it introduces another concept in modern FORTRAN. Those of you who are familiar with C will know that there is something called the C preprocessor. And if you see what I did here, qsort, you see here, this one you've probably seen in C. if defined debug, this code should be included. If it's not defined, this block is not sent to the compiler. So if I now say, first of all, we have to compile. We have to compile the reals. So I say, we put all in one go. I say GFortran C short reals. This is the function, and it's only going to be compiled as an object file. And means that if that returns 0, means it went well. It continues to take GFortran small one and qsort, and then it will run it. Can't open qsort? No, because it will probably require capital F. Yeah. Qsort functions, capital. And then we need to include the object file. No. Oh, strange. Never seen that before. I have another one. We can't really spend too much time on this. Aha. I've included the I included the qsort real function into I combined it in the same file. That's why it was 2 copies of the same thing. So now we'll have sorted. Easy. But if I now say qsort you see, if I now say include this one, if I now feed it this thing here, and it will print out a lot of debug information. But there's a catch here. Some of you might have noticed that I use capital F here for qsort capital F. If I were to have small f, it would not read, it will not use the preprocessor before starting. So if I do like this, and then it will complain even that it's not allowed, which is a good thing. But if I went the other way and say -f and give it capital F, it will read the debug information and print out the debug. If I remove the debug, So using the debug is a very, very powerful tool. It's been in C since 1972, I think, but it was introduced in the later versions of FORTRAN that you can have the C preprocessor doing it for you. I have an even more compelling examples further on. So I hope we managed to take elemental functions, and then maybe we'll have a break or we can continue. It's not much left. Elemental functions have nothing to do with elementary or simple or whatever. It is element by element functions that already covered in the vector syntax, element by element, but this time you write them yourself. This can make for a very elegant code. So this one will cover the quicksort. You have to play around with yourself. The only thing that add. The quicksort, you don't, so the quicksort, qsort, real. This one you don't really know. My mistake, that included it, sorry. So I removed the file. So my mistake. I was lazy and included it in, so I put them together in one file, so it's easier to compile. But this one is interesting. Elemental function. They are the element works element by element like this here. V plus U, V2, or V2, etc. Elements of V may be defined in a similar way. Side effects are permitted by using intention in-out and out argument. It's nice to see how the compiler work out the magic. We declare an elemental function a times b. It's called add_int because it adds two integers. Never leave home without implicit none. It's a question of life and death. Those who do intentional survive, those who don't crash in a nuclear fireball. Anyway, intention in is important. They are a and b are in. Integer add_int, of course, the function here is add_int, so that's the function. We add a and b together. This is kindergarten stuff. But here comes the nice thing. We write a program, and since this is an elemental function, we have to inform the program that it is an elemental function and how the parameters in and out works. So we need an interface block. It's also something new. We need the interface block to tell the program about the workings or the interface to this function. We need to tell it about the the parameters in and the parameter out and the intention. So we call it with two scalars. Of course, that's fairly trivial. We give it with two vectors, length 2. Then we feed it in two vectors with 3 elements in each. And then we feed it with 5 element vectors using implied do loops. So this could be interesting because this one only takes one A and B, and they are, you see, they are not vectors, whatever, they are just elements, single scalars, and we feed them with vectors, and it works. This is the beauty and magical things happen here, that the compiler actually fixed this for us. We can do better. We can say, I just enlarged the exercise a little bit so that it will it will also have higher dimensional. It's a matrix M 2 by 2, and it's a cube 2 by 2 by 2. And I did the same, but I just increased the inputs a little bit. You see here 2 by 2 matrices added together, element by element. And you see this was 2, and they are all 4s and they're all 2s. So, because I did the same. So imagine what kind of functions you can write here. This could really be something. Here you could really do something interesting things. We have half an hour left, or we should have been done it this a little bit earlier. We have come to the derived data types. Like a struct in C, derived data types. You can write your own data types. This one we covered. This is an important thing. Will derived data types. Demo 9. Derived 1. I have now the first one. I have a derived data type called myType, which also by coincidence takes an initialization value. I can give it an init value when I call it into, when I declare it. If I don't, I put it in a number 1 here, which if it's not given when I declare the variable, it will be given the number n. So I can say type type of type myType x, type of type myType with the argument 2. So the parameter value is 2. So this n here will be 2, and since it comes in here, it will not be given 1, it will be given 2. So we have a vector here, a is a length of 2. And if we compile this, of course, size 1, size 2, and I don't put any numbers in there, so it's 0. Could be actually anything, because if we just declare something like this, real AON, it could be any kind of number, but in this time, GCC has given it a number just and initialize it to 0. So if you go to the derived 2, you just see that it's becoming, I have derived 1 more data type. It's an allocatable, 2 dimensions, a bit more complicated, but just more of the same. Point is that it's an allocatable X. This one pointer, and there's no targets. So I have set this M to 1, to 2, and n equals, so on the derived 2, I can run this allocation. But what I'm thinking of here is something, looks to me something is not right. Yeah. Of course, no, it is right. I just was thinking that here it was a 2-dimensional, because I set the n equals nothing. For the pointer, it can't be, but here the allocatable one, I set n to 2 because n is just a fixed number, a single number, and n is the number of the length of that, and m is just a number. So M is just a number, which is printed out here. Z's M and Z1's M are 2 and 3. So here is using of pointers to print out. I set the A to Z and A1 to Z1. So A are pointers, Z are the targets. X is the allocatable ones. And of course, I can set either allocatable or target. It doesn't really matter because they are allowed to be pointed at. But I use something strange here, allocated by mol by Z. So I use the Z as some kind of mol that I use this as some kind of template or a mol to cast the X into. This one you have to read about here. It's nicely explained here. So complicated derived types are possible. Here I have the derived 3, which is just I just included a cube, X, Y, Z, and I can call it into here. I can call type cube 2 by 2 by 2. So it will be allocated in 2 by 2 by 2. And yeah, this is a bit tricky way of dealing with the derived data types because you don't normally need them to be initialized. But this is a way of taking two things in the same thing because there was limited time to go through examples. So I included the one with the initialization. You don't need to have that. So I think we have a derived 4. No, we're lucky. You got lucky. There's only 3 of them. Okay. That brings us almost to the end. But now we have generic functions. If you always wondered that you want a function that can take integers, real, double real, complex, and deal with them accordingly. So normally in the old days, you will have, the BLAST functions are mostly common for this. They have an S as a prefix for single, a prefix D for double, a prefix C for complex, and Z for double complex. That's very, view slideshow. This is very old fashioned. Wouldn't it be practical to call AX plus B and not Saxby, Daxby, Saxby, and Z Saxby? It would be easier if you could not call AX plus B, which you can, which is the last demo, number 10, which is also giving you some more interesting about using the C pre-prep processor. So we go to demo 10. This is the last demo, so I think we should finish also to have time. Also notice that it had capital F. That means that when this program is run, it will include the C pre-processor and do any macros I put in here automatically. Okay. There is a module. So now we are doing interesting things here. Module swap, SW2 is called. It have an interface. Swap. It's the name of this is the name, that's a generic name. Inside this module, there are swap real 32, real 64, swap complex 64, complex 32 and 64, and integers short and long. I use the C preprocessor to expand the macro swap A, B for me. That means that if I say GCC, I think it's P, I think it's just P. No. C preprocessor only. No, my mistake. Right. So this is a macro SWP. When this is called, it will be expanded by the C processor to do this. And this has nothing to do with compilation. This is just a text pre-processing. So it will actually translate any occurrence like here. It will replace with this. So if we go down here, you see in the source code, first of all, there is no mention of any define here, but the source code doesn't contain SWP in capital A times B. It's been replaced by this one. And the same here, because it's also there. So using macro in FORTRAN is very nice. So we now compile this one. And it's called F8, so it's 2808 standard. You see, it swaps 1 and 2 and 3 and 4. Swap A and B, swap C and D, swap X and Z, Z and A, and then it write out in a format. Another trick I played here, remember that when we were reading from the user, we read from something I refer to as an internal file, which is a buffer, text buffer. This one is a character of length 40. This is a text buffer, FMT. I set it equal to this one. I use it here to write here. So this is also seen before, but this is, yeah. Though I was wrong about the internal file. I have another one for doing this, but not in this one, because I have some places where this number here 4 is unknown, so you need to write it runtime. You have to write this text string, make this text string out at runtime. So this number 4 could be anything. This is a bit more tricky. Anyway, the swap routine, A and B are integers, C and D are integers, X and Z and Y are reals, Z and W are real, U and V are complex. And of course, we have 1 and 2 and 3 and 4. 1.1, 2.1, 3.1, they are swapped. The double precision numbers are, and these are double precision numbers, they are swapped. And the complex numbers are swapped. 6677, 6677, and 88. So by calling the same function with a different kind of input parameter works. And you can write that yourself. So the exercise I was talking about is to do the same thing with QSort. Make QSort work with double precision numbers and integers. Maybe expand it to do integers of both 32-bit and 64-bit, and even characters. So you can feed it character arrays and sort those, all with the same call to the same QSort. That concludes the first day of introduction to the modern things in FORTRAN. we can go over here and see if there's no more questions. So
Yeah.
word is open. So anyone has want to say something?
Yes, we will not add this part in when we publish the recording. So if you want to voice out, you can do it now.